In Chapter 3, we're going to look at the numbers of science. And it's really important that we make measurements and report them to the proper number of decimal places so that we're not telling people we can measure things more accurately or less accurately than we are. We're also going to look at scientific notation because frequently in science we're dealing with very, very small numbers or very, very large numbers. And so a useful way to represent those is using scientific notation. Dimensional analysis is also a really important tool that we use, and that allows us to convert between different units using the units to help us decide which mathematical operations need to be done. So it sounds like a complicated word, dimensional analysis, but it's just doing math using our units. We're going to talk about the metric system because in science that is the system that we use. And then how to convert between the English and metric systems so that you can see how the units compare. And then eventually we'll be talking about graphs and how graphs can be manipulated and what makes a good graph and a bad graph. Measurements are very useful in science, and we make measurements every day. And even though you may not realize it, you're making measurements in your life as well. So if you're cooking or doing construction projects, if you're sewing or doing arts and crafts, or looking at analyzing business data, you are making measurements and deciding on differences between those numbers. In science, we define different types of units, and units are exceedingly important to us. So we look at things like length, and we measure them in a meter. And we define what that meter is very, very accurately and very, very carefully so that when I talk about a meter, it means the same thing as when you talk about a meter. And so light is used, the speed of light is used to define how long 1 meter is. Time, we're very familiar with, and so time is measured in seconds. And the way that we define a second is based on a cesium atom and how frequently it vibrates between 2 energy states. So if you've ever heard of the atomic clock, what makes it atomic is those cesium atoms. Mass is the unit we use in science is a kilogram or a gram. So kilo means 1,000 times larger than 1 gram. And in the past, it has been a standard block of platinum that has been kept very, very carefully in France. And we'll talk about in just a minute how we're moving away from that. And just so you're aware, mass and weight are 2 different things. So mass tells us how much matter there is, where weight tells us how that matter is being pulled based on the gravity that it is in. So weight changes if we're on the Earth or if we're on the moon, but mass stays the same no matter where we're at. Another derived unit that we use is volume. And so volume, the standard unit is liters, and it comes from taking the length, the width, and the height of a particular object. So in the past, the kilogram was based on a solid cylinder made out of platinum and iridium, and it was kept in a vault in France, and it was called the kilogram because all other mass was based off of it. Well, there was a problem with this, and just a few years ago they changed the way they define it because that platinum cylinder compared to other ones that were supposed to be identical to it started changing in mass. So now what we've done is we've gone to defining it based on Planck's constant. And you probably won't notice any difference in the mass of things or how your daily life changes. But in science, this is a big deal because now it's not based on an object. It's defined now by the numerical value of Planck's constant. And so now we have a way to define that kilogram. And this is important when we're making very, very careful measurements. When we're making measurements, depending on the tool that we use, we can report different numbers of decimal places. And those different number of decimal places are based on the uncertainty of our tool. We write that by using a plus minus value followed by the measurement. So if we look at our two rulers, which one do you believe gives you the least amount of uncertainty? Well, if we look at our bottom tool, we know that we can read the ones place accurately. So we're going to put a 0 because we know that for certain. We're going to indicate where our uncertainty is by the first place that we need to do it, that we need to estimate. So we would estimate between the 4 and the 5. And so our uncertainty is in the 10th place of our reading. So we would indicate the uncertainty of this bottom ruler as plus or minus 0.1 centimeters. If we look at the top ruler, now we can read the ones place for certain. We can read the 10th place for certain because it is marked. And we're going to estimate between the 10th place. And so the uncertainty in this measurement is 0.01 centimeters because that is the first place that we have to estimate our reading. Now we cannot record more decimal places than that, and we should not record less decimal places than that. We want to record to that first uncertain digit. So here are some examples on how to record our measurements to the proper decimal place, including our uncertainty. So we can start with the uncertainty. We know that for the nail that is shown for us, we can read the ones place accurately. We can read the 10th place accurately. And our uncertainty or our estimation starts at the 100th place. So when we read our measurement, we want to make sure we're reading to the 100th place, the first place where we estimate. So in this case, we know that the nail is past the 5. It is on the 5/10 or halfway. And if it falls directly on the line, we need to include the 0, showing that we can make the measurement to that decimal place. So try recording the measurement and the uncertainty for the pencil. Well, if we start with our uncertainty, we know that we can read the ones place, the 10th place are marked, so our estimation is going to happen at the 100th place. For the pencil, we know we're past the 9 centimeter mark. It is on the 0.9 centimeter mark, and we're going to estimate that 100th place. It appears to be falling directly on that line, so I'm going to include a 0. What if it doesn't land exactly on the line? what do we do in that case? Well, that's where our estimation comes in. So we're going to look at the width of our bolt here. So we're looking at the ruler going vertically. Again, we can start with our uncertainty. We know that the ones place is marked on our ruler. The tenths place is marked. And so our uncertainty is in the hundredth place. Now, if we look at this, we're not quite to 1 centimeter yet, so it's going to be a 0. We're past the 5. And then we estimate. We split the space between marks into 10 equal spaces mentally. So this looks closer to the 0.5 than it does the 0.6. So I would estimate this to be 0.52 plus or minus 0.01 centimeters. Now, if you estimated it as 0.53 or 0.51, that is perfectly fine. That's why we have uncertainty in our measurement. All right, let's look at the length of our bolt. Okay, the ruler, again, you can read the ones place and the tenths place. We estimate at the hundredth, so that is going to be our uncertainty. We're past the 3 centimeter mark. We're between the 0.1 and 0.2 centimeter mark. And we're not quite to the 0.2, but almost. So I would put a reading of 3.19 plus or minus 0.01 centimeters. And again, if this isn't exactly what you got, but you were very close, that is perfectly fine. Here's one for you to try. Pause the video, estimate what the uncertainty is going to be and what your measurement would be. So let's look at what we can read. So we know the ones place. We have marks for the tenths place, but we do not have 10 equal marks between the tenths place. And so our estimation still happens between the tenths place. So even though we have a few more marks on this ruler, our uncertainty remains the same because it's not equally split into 10 equal spots between the 10th place. So our uncertainty is still in the 100th place. Our measurement, we're past the 3. We're between the 0.4 and 0.5. Now we have help because we have the halfway point. And so it makes our estimation a little bit easier. And I would estimate this to be 3.44 plus or minus 0.01 centimeters. In the lab, we frequently use something called a graduated cylinder. Graduated because it's marked with measurements. And the liquids that we put in these graduated cylinders usually are attracted to the sides. And what happens is we have something called a meniscus. So it is that curved line of the attraction of that liquid for the glass. When we're making measurements, we read at the bottom of the meniscus. So how would we read this measurement? What would our uncertainty be? So let's start with the uncertainty. We have the tenths place marked. That means that each line between 60 and 70 is going to be the ones place that we know for certain. We don't have marks between it, which would be the tens place, and so that's where our uncertainty is. So if we're reading this, we know it's past the 60. It's about the 7, and I would say it's right on that line, so I would record a 0. And this is not centimeters. When we're measuring volume, it's recorded in milliliters. Here's another one. So we have our meniscus. We read from the bottom of our meniscus. Our 30 and 40 are marked. So we know it's above 30. We look at the lines. It is above the 6, between the 6 and the 7. So I would estimate 36.4 plus or minus 0.1 milliliters. We know it's 0.1 because our estimation happens at the tenths place. Now, when we're writing numbers that are very small or very large, we use something called scientific notation. Simplifies the way we write those numbers. We have a coefficient that is at the front, and that falls between 1 and 9.9. We have a base unit, and then it is always times 10, so we're always raising it or using times 10 as our base unit. And then we have an exponent. That exponent can either be positive or negative. It's positive when our numbers are larger than 1. It's negative when our numbers are smaller than 1. So when it's a decimal, we're going to have a negative exponent. So if our number is larger than 1, that exponent is determined by the number of times you have to move the decimal point. So we want our coefficient to be between 1 and 9.9. So in this case, our coefficient is going to be 9.4. We're going to include that base unit of times 10. And to figure out our exponent, we see how many times we move it. So 1, 2, 3, 4, 5, 6, 7, 8. So our exponent is times 10 to the 8th. It's positive because it's larger than 1. Now, if we have smaller than 1, we're going to put our coefficient 8.76 because it's between 1 and 9.9. Put our base unit times 10, and then we see how many times we have to move our decimal point. 1, 2, 3, 4, 5. Because we went to the right and it's less than 1, it becomes a negative. See if you can put these into scientific notation. Pause the video and put in scientific notation or write it out into the expanded full number notation. All right, so for our 83,400,000, we want it between 1 and 9.9. So it's going to become 8.34 times 10. We're going to the left, so it's going to be positive 7. Here we have scientific notation. Now if we're going to write this out, it's a negative number, so I know it's less than 1. I need 6 digits. So 1, 2, 3, 4, 5, which is 5 zeros, and then the 3 that we move the decimal point. Okay, so now we have a number that is less than 1. Our coefficient is going to be 5.6 times 10. We're moving to the right, smaller than 1. And we moved 10 places, so it is times 10 to the negative 10th. If we write this, our 2.09 times 10 to the 8th, we're going to have to include 6 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, which is a total of 6 zeros that we've added to get to our expanded number. Being able to use your calculator properly is very important. You want to check to make sure that you can come up with the correct answer using scientific notation. So pause the video, try to calculate the answer to this problem. The answer to this problem, 3.78 times 10 to the 20th. If you did not get that answer, double check your calculator again. We can estimate if we multiply all of our coefficients together, we end up with 3.78 by looking at our exponents. We can take 22 plus 2 plus 19 minus 15. And then we would have to, because it's in the denominator, we would subtract 12. We would subtract a negative 8 and subtract 4, and we come up with 20 as a double check. Now, if you're not getting the proper answer, you want to make sure that you're putting parentheses around that denominator.